What percentage of dark matter enters our body? What if we told you that one of the universe's most mysterious and abundant substances is going through our bodies at a rate of every second? By now, you may have figured that it's dark matter, and you'd be right. Planets, stars, galaxies, and other objects that we can currently see make up only 5% of the universe. The remaining 95% is made up of dark matter and dark energy. And it is continuously moving through our bodies. How much, though? Does it affect us in any way? Well, we'll respond to them in this video and other inquiries. You must have a deep curiosity about human spaceflight and the secrets of the cosmos if you are here watching this video. We work hard to create content that will intrigue someone as curious as you, so subscribe today and enable bell notifications. Now let's return to our dark matter. Our cosmos doesn't fully make sense, despite the presence of planets, galaxies, stars, and other objects. If we examine the Milky Way, our own galaxy, does it not possess sufficient mass to hold all star systems together in the shape of a spiral galaxy? Nonetheless, it persists. How so? On the grandest of scales, the same thing occurs, the same narrative can be found everywhere. There isn't enough stuff in the universe to explain the gravitational forces we see. What then could be the reason for the galaxy stars and planets to cluster together? Scientists coined the phrase dark matter to address this. We are only able to recognize its consequences because we are unable to see it. Since it is dark, no visible celestial bodies such as planets or stars can be seen. The universe has far too little visible matter to account for the 27% required by the measurements, according to the observations. Second, it does not exist as a collection of baryon-based particles known as ordinary matter's dark clouds. We can detect baryonic clouds by measuring the amount of radiation that is absorbed by them, and we have discovered that they do not interact with any electromagnetic radiation. Finally, dark matter is not antimatter because we cannot observe the recognizable gamma rays that result from the collision of antimatter with matter. The hidden matter in galaxies is explained by dark matter, which is now known to be present in almost all galaxies. With a mechanism known as gravitational lensing, we have verified the existence of dark matter. Since dark matter is invisible to the naked eye, astronomers must instead study how the gravity of giant galaxy clusters that include significant amounts of dark matter bends and distorts the light of more distant galaxies that are located behind them. Large galaxies, massive galaxy clusters, and eventually humankind are created when matter collects into clumps. We wouldn't exist without dark matter. None of this would be conceivable without the presence of nearly 5 times as much matter as protons, neutrons, and electrons can account for. Dark matter is necessary for the normal operation of our universe. Furthermore, if dark matter exists, our Milky Way must likewise have a halo of dark matter, and some of that matter must flow through the solar system, the Earth, and perhaps even you. How much, though? Let's look at it. Everything was hotter, denser, and more uniform in the early cosmos than it is now. Early on, there were patches with a little bit higher density than usual, indicating a larger than average amount of stuff. More matter is drawn into such an area by gravitation, but radiation forces it out again. The galaxies and galaxy clusters that we currently observe would be very different if simply ordinary matter and its component particles were to travel with this radiation. The galaxies and galaxy clusters that exist now would be very different from what we view if all we had to work with was ordinary matter and its component particles. Dark matter indicates that there will be a vast, diffuse halo of dark matter around any significant structure in our universe, such as galaxies or galaxy clusters. Because normal matter may collide and interact with both itself and radiation, it will gather at the innermost regions of each galaxy. In contrast, dark matter just goes through everything, including itself, ordinary stuff, photons, and so forth. Dark matter particles only interact gravitationally because they are unable to lose the significant momentum they begin with. In the span of the universe, a single dark matter particle may have barely made a dozen trips to the galactic center. On the grandest of sizes, dark matter rules the universe. But where we are located, at 25,000 light years from the Milky Way's core, regular matter predominates over dark matter. In our solar system, on Earth, the condition is a lot worse than it is in interstellar space. Humans have a density of 1,000 kilograms per cubic meter, which is the same as water. The local density of dark matter where we are is significantly lower, at roughly 10 to 21 kg/m3, if we look at the most accurate models we can create. The total amount of dark matter present in every person on Earth at any given time would be less than a single nanogram if we totaled it all up. All of the dark matter in the solar system, including the region beyond Neptune's orbit, would weigh just around 1,017 kilograms, or about the mass of a sizable asteroid. It also doesn't move with the solar system because it doesn't interact with other things like normal matter does. Not only that, but it doesn't even circle around the disk of the Milky Way. It doesn't travel around the other stars or the galactic center. It doesn't even orbit the sun. Simply said, dark matter travels at extremely high speeds in relation to Earth while being affected by gravity. In other words, this substance moves pretty quickly as compared to Earth when it is affected by gravity. You only need four numbers that you can multiply together to determine how much dark matter travels through you in a certain amount of time. There are four factors to consider: the dark matter density, the human body's surface area that it can strike, the dark matter speed, and the length of time you need to know the answer. We already know the dark matter density, which is 10 to 21 kg/m3, so once we've estimated it, we can immediately find the solution. An average human has a surface area of 1.7 square meters. We can quickly calculate the region that the dark matter sees and find that it is more likely to be 0.6 square meters because the dark matter enters at a random angle. Although the galactic center is orbited by our solar system at a speed of about 200 kilometers per second, infalling dark matter should be traveling at a rate closer to 350 kilometers per second. In total, this indicates that dark matter travels at a speed of about 400 kilometers per second when compared to an Earthling. And we can do this at any time, whether it is once every second, once a year, or once during an average 80-year human lifetime. Even while you only contain 10 to 22 kilograms of dark matter at any given time, significantly higher volumes are constantly circulating within you. You will experience 2.5 10 to 16 kilograms of dark matter traveling through your body every second. 10 to 8 kilograms of dark matter pass through you on a yearly basis. And a total of slightly about 1 milligram of dark matter has traveled through you in the course of a human lifetime. Even a seemingly insignificant sum can add up over a sufficiently lengthy period of time. The fact that these numbers are so big informs us something about our bodies and what's inside of them, as well as how we can imagine looking for dark matter in the future. We are aware of the mass of dark matter that can pass through any detector in a given volume, regardless of whether it is composed of extremely low mass or high mass particles. The number of particles that pass through anything can be calculated if we assume to know the mass of dark matter. We have been developing more powerful and sensitive detectors for decades in an effort to study any seemingly insignificant interactions that might exist between dark matter and normal matter. Today's most sophisticated detectors search for indications of a rebound or other contact using atoms with massive nuclei and incredibly huge masses. And all direct detection methods have thus far been ineffective. To the best of our understanding, dark matter is present everywhere. Even if it isn't visible to the human eye, we can nevertheless feel its gravitational pull. It moves through every piece of substance in the universe, including people, as if it weren't even there. To the best of our knowledge, there aren't any collisions or interactions besides how it affects how space-time curves. Like black atoms or molecules, it doesn't clump, cluster, or create any kind of structure. But if it even has a remote chance of colliding with radiation or ordinary stuff, we will be able to detect it. A milligram of dark matter will have traveled through your body during the course of your life. We will have a chance if even one dark matter particle interacts with a single proton or electron in your body. It's difficult to ask for more when it comes to dark matter, one of the universe's greatest mysteries.